All right, so good morning. So let's start our very brief journeys to elliptic curves. So basically, elliptic curves are in the central of pure math because it is just related to everything. So of course, it is a curve, so it is basically a geometry. And it turns out that it also has a natural algebra structure. And also there are complex analysis involved. And elliptic curves, being a curve sometimes with just integer coefficients, will be related to number theory by looking at mod p of all those integers, for example. Yeah, so basically elliptic curves, the study of elliptic curves relate four main areas in pure math. So if you really want to have a deep understanding of this, you might usually take at least 1 year of PG level course to do this, and we are going to do this in one lecture. Just just a very brief overview of what's going on here. So kind of to be more precise, well, elliptic curves are defined by equations on a space. So it naturally has a geometry, but it turns out that it's more related to topology. So it actually looks like something like a torus. So torus is like a donut shape. So topologically, elliptic curves are genus 1 thing. So torus is genus 1, which means you have one hole. And then because it is a torus, somehow naturally you will get a group structure out of it. So the torus will give us a group structure so that elliptic curves, even though they are just equations, have a very non-trivial way to do addition. Abelian group structure. So there's an algebra here. And then as we mentioned, there's this number theory. So number theory basically look at, say, rational points. So what points on the elliptic curves have rational coordinates? So the study of the rational points of elliptic curves is part of the main thing in number theory. And of course, you can also talk about mod p stuff. And it turns out that using this kind of information, you can define the L function, just like what we did in chapter 7. So you have because you can talk about mod p is prime. So you can talk about product over p of something and use this to define an analytic function, which is called L function. And so the whole study of elliptic curves basically are surrounding the relationship between these four areas. And in particular, today we will talk about the BSD conjecture, which is one of the $1 million unsolved problem that relates analysis and algebra of elliptic curves. So maybe I should, let me swap these two. Let me swap these two. Yeah, and then I can draw here the relationship between these two is the celebrated BSD conjecture, which is the $1 million problem. So between analysis and algebra. Yeah, so why elliptic curves are so important and special? We can start with some motivation before we talk about the definition. So let's just look at quadratic equations. So we have quadratic equations, the most in two variables. So the most general form, you can have quadratic terms, you can have linear terms, you can have constant, right? So this is the most general quadratic equations in two variables. And you can do some kind of change of variables, right? For example, you can do x minus, I don't know, the completing square thing, b over 2a, something like that. So you can do completing square and eliminate some of the terms, right? So at the end, after you do a lot of simplification, these equations, let's say here is over R, so the coefficients are real numbers. So after all these simplifications, basically you will get 3 different classes of equation. You either get an ellipse, or you get a hyperbola, ellipse, singular, ellipse, hyperbola, and what else? You also get parabola. So these are known as the conic section. So everyone should know this, I guess. I guess from high school. So circle is a special case of ellipse, so I don't write circle. So circle are ellipse with same size of x squared and y squared. And you can rescale x and y, so this is one kind of change of variables. If you can rescale x and y, you can turn ellipse into circles also. But anyway, so these are the three main class. And we note that sometimes you cannot, basically you cannot translate from one to the other. So for example, if you have a circle, you can never get to a hyperbola, right? So no matter how you change variables, you cannot change circle to hyperbola. Basically, because the signature or the quadratic form of this equation is not preserved, right? So these are the best three case you can do in quadratic. But how about one dimension higher, one rank higher? So what about cubics? So of course, quadratics are all well-known, well-studied. Everything is known about that. So definitely we want to do one rank higher. So what is a general cubic? So you have cubic term, and then you have the quadratic term. So many terms. And then you have linear term, and then you have constant, right? So you have a long chain of thing of coefficient. Let's say over R over Q. Yeah, let's do over Q because we are interested in just like integer coefficients. So all these coefficients are say rational numbers, or you can clear denominator. You can assume all these coefficients are integers. Right? So this is a general cubic, right? So the question now is, can we simplify it by some kind of change of variables to some class? And it turns out that you can most of the time. With one additional assumption is that first of all, this has to be non-empty. Right, so that means at least one point lying on the curve. So if your field is complex numbers, you can always just plug random points here. But in general, say if you just look at rational points, then there might not be any integer solutions to this. So let's just assume we have one point, say P. Then it turns out that you can do a so-called rational transformation. So there exists a rational transformation, which can be easily described using geometry. So rational transformation means you take x to be some rational number, rational thing of this type, divide by, I don't know, delta x. What's the next one? X. Theta, right? So expression like this. So linear over linear, linear over linear. So that's the rational transformation. So and the same for y. So it turns out that you can always find appropriate coefficients such that the curve is transformed into the following form. So these AB are not the same as the previous AB. So just this form. A very nice one. So yeah, so there's a simple algorithm. So if I can spare like a single minute. So if I have a curve, so I will see later the shape of this curve. So basically you have this point here. So let's pick a point here. Let's call this P. So we can draw tangent line. Tangent line. So this linear thing. Some x plus some y equals some constant. So let's call this f, the function f. And then you draw another tangent line and call this g. So g is an equation. And then finally, you pick arbitrary line that pass through P, you call this H. Then your transformation is given by G over F and H over F. So that's how you compute this linear thing. So G is the tangent line to that point. F is tangent line to P. Y is H is any point, any line passing through P. So if you do this transformation, then you will have some magic happens due to geometry reason, and you get to this simpler form. And we can do further simplification. So now if I multiply both sides by x, and let y to be xy, so we can see that this becomes y squared, right? And then this becomes ax plus by equals cube square x. So I multiply both sides by x and then redefine my variables. And finally, the left-hand side, you can do completing square to simplify to cancel the linear term. So you can shift y to cancel the y term, and you can also shift x to cancel the x squared term. So at the end, after all the shifting, you will get y squared equals x cubed plus ax plus b. So that's the Weierstrass normal form for cubic. And this is an elliptic curve. Right. So the whole discussion is saying that given an arbitrary cubic, like above, you can do very simple transformation and turn this equation into this canonical form, which is called the Weierstrass normal form. And so the study of anything in two variables on cubics will be equivalent to studying elliptic curves. That's why elliptic curve is so important, because it basically is the only family in the degree-free world that you need to study. Instead of like quadratic, you have hyperbola, parabola, ellipse, you have free class. Here, you only have just one single class. Yeah, so as a simple example, let's say I have a cubic like this, so very simple, a cubic like this. Then the above, you can try to follow the above procedure, and you will see that if I substitute x equals, let me see, 12a over u plus v, and y equals some crazy number. So basically, u plus v is the f in that picture. So if you do this substitution, then this will become y squared equals x cubed minus 432a squared. So this 432 always appears in elliptic curve theory. Yeah. So any cubic can be reduced to this canonical form. So this always happens. So let's just have some basic example. So y squared equals x cubed plus x plus b. So the simplest one, the typical shape of elliptic curve looks like this. So either, because it is a cubic on the right-hand side, either you have one real root or you have three real roots, right? There are only two situations. So the left-hand picture are the situation where you have one real root. So it looks like that. And if you have three real roots, then it turns out that the curve are usually split into two components, a little egg-shaped thing, and also a infinite curve. And this curve, remember, it is a cubic curve, so actually it is like very fast going. So any like linear line will eventually cross it, because linear is not faster than cubic. So these are the situations. But of course, if I change the coefficients in a continuous way, then I will be able to change from one graph to the other graph. But at some point, there will be some kind of singularities, right? So examples of this type. So the first one, you will have like a sharp point. So these are called the cusp of the elliptic curve. So it is like a sharp point, which means it is not differentiable there. bad thing. And you might also have self-intersection like this. So you have like a cross. You have like a cross in the y-axis. So these two conditions basically means that those points are not differentiable. And you can write down the condition for this, and it turns out that it is equivalent to the discriminant delta, which is 4a cubed plus 27b squared, not equals to 0. So equals 0. So bad things happens when delta is of this type, which kind of means that the cubic has like double root and the usual quadratic meaning of discriminant. So you don't want these things to happen in general. So this condition means the curve is non-singular. And so you can differentiate the curve everywhere. Yeah, so for example, you can check that the left-hand curve, A is 0, B is 0, then of course this is 0. And for the right-hand curve, A is -3, B is 2, so this is also 0, which is the bad situation. Yeah, so for technical reason, we usually assume discriminant is non-zero. Yeah, and also another slight easy observation is that this curve is definitely symmetric along the x-axis because, well, it's y squared equals something. What do you expect? Y squared equals something is always symmetric on x-axis. Yeah, so studying this curve, kind of like you just need to know what happens in the upper half of the curve. So that's the first motivation, that every cubic thing is elliptic curve. Well, but actually, I've hide one more thing, is that because we are dividing, right? This transformation, we are dividing by something, so there might be infinity. So in general, we would like to study elliptic curves not as it is, but as a projective thing. So usually, for those who know projective geometry, as projective curve. So basically, we allow a single infinity point. So we allow infinity points here. If you don't like infinity, then basically you homogenize this equation. So you multiply Ez appropriately. So you get EZY squared, x cubed, ax Ez squared, b Ez cubed. So make it like all degree free. And then you can allow Z to be 0. So yeah, so there will be a single infinity point. In the picture, will be something like above infinity, far away thing. You can think about this way. So that's the first motivation. Now you might ask why this is called elliptic curve. Where is the ellipse? Where is the ellipse? There's no ellipse here. And this is not an ellipse. This is an egg. This is an egg. It is not an ellipse. And we also know that it looks like a torus. Torus does not look like an ellipse. So where is the ellipse? Right. So that's the second motivation. Please. So the second motivation is why it is ellipse. Well, it comes from finding the arc length of an ellipse. So you probably have seen this in 1014 or 24 to set up the integral to find arc length. So if I have a general ellipse, then the arc length is given by this integration. So everyone should have at least one experience at some point to set up this integral, not evaluating, just set up this integral, right? And of course, if a equals b, this is just the perimeter of a circle, and you can make it 2 pi r, right? But in general, this is how you set up the equation. And to solve this integral, you do substitution. Right? So I simplify the substitution. It is of this form. So this number is usually called the eccentricity. The circle has 0 eccentricity. So square root of this term is eccentricity. So if you do this substitution, then the above integration becomes this expression. And this is a elliptic curve, right? Because the bottom part really is just y equals square root of some cubic. Or in other words, y squared equals cubic, which is elliptic curves. We have just learned this. So elliptic curves are really related to finding the arc length of an ellipse. And this kind of integration is called elliptic integral. So for those of you who are in my 1024, you have already did this in one of the homework questions. Or optional, I forgot. Optional or? But anyway, yeah, so these are elliptic integrals. So finding arc length of ellipse means finding integration of some elliptic curves. So that's the reason why these things are called elliptic curve. But actually, we can do a bit more analysis on this. So that's the third motivation. New slide. Because these are like curves. So what happens if I want do 1 degree lower? So what happens if that is just a quadratic? If that is just a quadratic, we all learn in 1014 how to evaluate them using arcsine, right? So the third motivation for elliptic curves is that we want to find a parametrization. So if we just look at the circle, this can be parameterized by like simplest case, sine t, cosine t, right? Everyone know this. And also this is like periodic function, both are periodic functions. And how can we relate this to that arc length problem? Well, I mean, of course, when you try to compute the arc length of a circle, you can evaluate the integral directly, or you can throw the professor and rewrite in a certain bad form and do that. So it turns out, for example, you can compute this expression. So what is the answer? Well, I mean, this part looks like y square plus t square equals 1. So it looks like the original curve, right? So we know what is this function from the integration table. This is arcsine function. This is arcsine. So somehow the sine function is the inverse of this, right? So this is the inverse function of this expression. And cosine is the derivative of that. And you can actually see that in general, if you have a curve like y equals fx, then this expression, ft, the inverse of this expression, so let's say f is the inverse of this, and f prime, these two will be a parametrization of the curve. So this will satisfy f prime equals f of f. Basically, you just use chain rule. You just use chain rule to differentiate f. You see that the result, well, differentiating the inverse is 1 over the derivative of the integral, which is 1 over ft. So 1 over is ft. But then you have to plug it back the inverse, the f function. So you basically see that chain rule tells you f prime and f satisfy this. So it is a parameterization of the function. So in particular, if I do the same trick for the elliptic integral, that is my function f. But I mean, just don't care about the range. I mean, x above or below is just like up to a minus sign. So if I do the same trick here, then we see that if I somehow have a inverse function of this integral, and then the derivative will give me a parametrization of elliptic curves. So I can kind of formally say that if I can now define inverse of, and we use complex variables of elliptic curves, so cubic. Then this will give me a parametrization of my cubic curve. And this is known as the Weierstrass P function. So if I let's say I let U to be this, then the Weierstrass P function, I have to be careful about the notation. So it has to be this thing. So it is the inverse function of U. And the general theory about tells us that this function and the derivative function is a parameterization of the cubic curve, but now in the complex world. So we allow complex argument also. So both x and y and y and let's see, both y and c are complex, can be complex. X and y can be complex. Yeah, so this is how, in the abstract case, to compute the parameterization f, just like sine and cosine. Now we have p and p prime. And so here we have periodic. It turns out that, again, magically, this p function is also periodic. But because it is a complex function, it is not just periodic in one direction. It is actually periodic in two directions. So these are actually doubly periodic, which means that the function, if you add one direction, the other direction is the same as itself for linearly non-independent vectors. I mean, linear independent in C. So in the complex plane, you have two different complex numbers that are not parallel. And so this function turns out to be doubly periodic. And this is the starting point of relating elliptic curves to torus, because torus, the donut thing, can be thought of as periodic in two directions also. And so basically, the P function defines a function on the torus. So that's the last motivation before we jump a bit to the technical details. Okay. So torus, elliptic curves is torus. That's the second kind of session. So even though it looks like this funny little shape, it is just a torus over C. So what does that mean? Well, we have y, let's write again. So we have y squared equals x cubed plus ax plus b. So now if I imagine this as things in complex numbers, what does that mean? That means we are talking about a subset of complex squares, so two complex numbers with one equation. So it means that I have a complex curve in C2, right? I mean, 1D thing in 2D, by definition, is a curve. But this is a complex curve. Complex itself is a 2D thing. So you can also think of this as a 2D surface inside. Basically, you have two variables, you have one equation, so you have 1D thing, but this 1D thing is a 1D over C, so it is 2D over R. So geometrically, elliptic curves looks something like a 2D surface in C2. And so the claim here is that this 2D surface is topologically a torus. So, and yeah, so the curve itself, remember we still have to add this infinity point. So I should also add infinity point to kind of close it, like a compactification thing. Yeah, so I should write here the elliptic curves over complex number, by definition, will be all the point in C2 such that y squared equals x cubed plus ax plus b together with a single infinity point is a torus. So that's the more precise statement. So what is a torus? Do I have a picture? Oh yeah, I have a picture, yes. Yeah, so torus, this is torus, okay? A donut, 2D real thing. And torus has two circles, longitude, latitude. There's two circles. So in maybe high school, I don't know, in high school or not, usually we can present torus as like a square, and then you identify two sides of the square, right? So this is somehow how we visualize torus in topology. So we basically wrap the square, so you get a cylinder, and then you wrap around the cylinder to get the torus, right? But to be more precise, we can actually consider the C2 plane, so the complex plane, and then choose two directions, omega1 and omega2, and then use this as my square, right? So that a torus basically is this square, but then you can also extend to the whole plane by identifying periodically the points in the plane. So for example, this point here will be the same as this point, will be the same as this point, will be the same as this point, and so on. Well, I think it's in one of your homework too, the lattice. Well, homework 3, right? The lattice thing. Yeah, so it's similar idea. So you basically identify all the periodic points into this parallelogram. So this blue part of the parallelogram really is the surface of this torus. And so these 4 points, all these 4 points corresponds to like the same point on the torus. Yeah. This point maybe on the torus, because they are periodic. So these are the same point, considered to be the same point on the torus. So in such a sense, usually we can write down the lattice. So the lattice is the integer span of the two directions. So the big dot of this diagram. And so the torus can sometimes be considered as the complex plane portioned out by this lattice. So 2 points are considered the same point if they differ by an integer multiples of omega1 and omega2. Right? Yeah, so if you have a lattice, then you can also have sublattice, or is it called sublattice? Or the bigger lattice. So for example, 1/4 of this lattice will be the 1/4 point inside the parallelogram. So it's like another lattice sitting inside. So it will correspond to like this grid here. Right. Yeah. So we can also talk about that. We'll come back to this later. So we have torus here, which is something that is omega1, omega2 periodic. We also have the p function, which is omega1, omega2 periodic, which means the p function is a function on the torus because it is well defined. If you have different points differ by integer multiples, you get the same value of p. And it turns out that this p is exactly the isomorphism between torus and elliptic curves. So let me write down the main statement. So first of all, we actually can have a explicit expression of the p function. So the Weierstrass p function is defined to be the following. It's 1/c squared plus all the points in the lattice without zero of this expression. So it's an infinite sum. It is an infinite sum. It converges absolutely on all the z that is not on the lattice. Because if z is on the lattice, then you get 1/0. You don't want 1/0, right? So if it is on lattice, then you get a pole of order 2. Well, I mean, it's 1/c squared. So of course, pole of order 2. Yeah, so there are basically two situations. If z is not the lattice point, this is an absolute convergent series. You get the actual value of that. If C is on the lattice, then you get 1/0 squared. So it is a pole of order 2. But in any case, this is a meromorphic function. Nice one. And also, by definition, it is doubly periodic. Because of that definition, you just shift your summation. And furthermore, you actually can compute the derivative easily, term by term differentiation, because it is absolute convergence. You can term by term differentiation, you get a very nice expression. To the power of 3, I think. So the cubic appears, cubic and square appears as we want. So now these two are things that is good away from the lattice, bad when it is on the lattice. So if you have some combination of them that cancels the poles, then you get an entire function on a compact thing, on a bounded thing. So Liouville's theorem from compact analysis says that it must be a constant. And so we can actually solve for this constant. So let me write down the actual expression. So the Weierstrass function can be written as a power series at 0 of the following form. Well, because I mean it has a simple pole at 0 only. All the rest should be analytic. So you get a power series of this form. So these numbers are called the Eisenstein series. And it has a nice expression also. It is just this one. And defined for n bigger than 3. So you just sum up over all the lattice points. And it converges when n is bigger than 3. And then we define G2 to be 60 of G4, G3 to be 140 of G6. Then we will get an ODE. This square equals 4 cubed minus G2 minus G3. So it satisfies a elliptic curve. This is an elliptic curve. So as promised, P and P prime are exactly the x and y of an elliptic curve. And this is a isomorphism. So the main theorem, we have an isomorphism from the torus to the elliptic curves complex point on the elliptic curves. So this is y squared above is like what? 4x cubed minus G2x minus G3. So if I have a number here, I just send to x and y. Right. If C is not on the lattice. And remember, when C is on the lattice, we get a pole. So we just send this to this infinity point. If C is in the lattice. So that's why we need this extra infinity point. So for those who are familiar with projective geometry, so in terms of projective space, we actually send things to P prime 1 and 0, 1, 0, respectively. So that if you want to avoid using infinity, I should use the colon notation. Right. So now we have a parameterization, but now the good thing is that we have torus, and torus is not just any surface. Torus is so special because it has 2 periodic directions, which means you can add points on torus, right? If you look at this picture again, I can actually add 2 points. So if I have this point and I have this point, then I can add them just like how do I add like this? So by parallelogram law, you can get new points on the torus. Even it is outside the bound, right? So if I have this and that, for example, then parallelogram law tells me I get some point somewhere here. But then because of the periodicity, this is really this point, for example, right? So I can add 2 points on the torus and get the third point on the torus. Torus is an abelian group. So torus is just an abelian group because you can add 2 points on the torus, you get back something inside the torus by this periodic lattice. So it turns out that this is not just any isomorphism. This is actually a group isomorphism. Because torus is an abelian group. And with this, we have algebra. So on the left-hand side, we have an abelian group. And now we have a map. So this means that I can carry the group structure on the left-hand side to the right-hand side. So now by brute force, I would say by brute force, if I have A plus B on the left-hand side, then I send the image to the right-hand side. I just call that A plus B in the right-hand side by brute force. And even though this looks so arbitrary, it turns out that this group law on the elliptic curve side has a very, very simple description in terms of just drawing lines. So how do we draw lines? I have a picture. Let's look at this picture. So no, I actually have a picture. I'll just write this. So we have group law on elliptic curves. And actually, because complex numbers are bad, so let's just look at real point or rational point, so I can actually draw the thing. So if I have 2 points on the curves, then I can join PQ, intersect at R, and define P plus Q to be the reflection of R. And also, I will just set 0 to be the infinity point of my group. So let's look at the picture. Yeah, so this is from Wikipedia, of course. So basically, if I have a point P here, point Q here, I draw the line, I get R, right? And then I look at minus R, which is here. And I just call this minus R my result of P plus Q. And that's why Wikipedia say P plus Q plus R is 0. So this is my minus R, will be P plus Q. And we also call 0 the infinity, so that in this picture, for example, this is really minus P. So P plus minus P, if they lie on the same vertical line, of course, there is no third intersection. And we just say that it intersects at the infinity. So infinity, in some sense, will be my 0. So infinity will be the 0 of the abelian group. So there are 2 more special cases. For example, what happens if I want to add Q plus Q? How do I add Q plus Q? Well, I can't talk about the line joining Q and Q, but we can just use limit and call the line joining Q plus Q the tangent line at Q. So here, the tangent line at Q is the Q plus Q thing. So Q plus Q will be the intersection of the tangent line to P, and then you reflect. So this is Q plus Q, or 2Q, by definition. And of course, the last one, P is also a point with tangent vertical. So P plus P in this case, we have no intersection. So P plus P is 0. So we say that in this case, for example, P has order 2. But 2P is 0. So you can actually see that in general, 2P is 0, if and only if the y coordinate is 0. because at y coordinate equals 0, you must have a vertical tangent. So p plus p is the vertical tangent. So it has no intersection. So the answer is infinity, which is 0. Okay. So in general, we call a point finite order. Finite order if p plus p m times is 0. And here I give you another non-trivial example. This one. So this is a non-trivial example. So we start from p. Say we start from p. And what is p plus p? P plus p is the 2p. So you take the tangent line, intersect here, and then we reflect. So this is 2p. And what is 3p? Well, 3p is p plus 2p. So we just join the line and then reflect, but because it already lies on the y-axis, we don't need to reflect. And 4p is p plus 3p. So we have 3p and p. So the line intersect here. So we get the reflection is 4p and so on. So you see that in this case, 6p will be 0, right? 6p is p plus 5p. It has no intersection and it becomes infinity. So in this case, 6p is 0. And you can notice that this p actually has a coordinate. It is 2 and 3. I mean, 8 equals 9 equals 8 plus 1. So this is actually a very important result in elliptic curves theory. So this is the first main theorem with a name. So it's Nagel-Newton's theorem. So it says the following. So we have y squared equals x cubed plus ax plus b. And we assume the integer coefficients, and we assume it is non-singular, right? Then a rational point, has finite order if and only if it is integer. If it is integer. So if you have a rational point in this curve that has finite order, then you either have then you must have y and c both integer. And actually, there are only finitely many of them. Either y equals 0, which we have seen means the order is 2 because it lies on the vertical tangent, or y divides the discriminant. So in particular, only finitely many. Discriminant is just an integer, so you just count how many y divides delta and check case by case whether it is finite order or not. So there are only finitely many points with integer with finite order. But that means all the other points, all the other rational points, must have infinite order, right? So you keep doing p, 2p, 3p, 4p, 5p, and so on. You never get back 0. So this is the main theorem before the break. So this is the model theorem for elliptic curves. So it asks how big is this thing. So this, first of all, this is an abelian group. It's abelian group. So the theorem says that if E is non-singular, so the discriminant is not 0, then this group is actually not that big. It is finitely generated. So if for those who are in 3131, then you should know that finitely generated means that my group is isomorphic to some power of the integers and then a finite abelian part. Right. So this finite abelian part is exactly the Nagel-Newton's theorem that we just mentioned. Right. So the finite abelian part is exactly all those points that has finite order, and the rest actually will be a tensor direct sum of just integers. So this R is called the rank of the elliptic curves. So this is the first main definition. And in general, this is not true for singular curve. Not true for singular curve. So for singular curve, you can have infinite thing. So the meaning of this basically is that we can find all rational points of E by starting with a finite set. It's finite set. And then plus that tangent line intersection procedure. Yeah, so this is the main important thing. Elliptic curves has a very nice group law, and it has a very nice set of generators. Unfortunately, it is still an open problem how to find R and the generator. So in general, there are no known algorithm. I mean, efficient algorithm to find R and the generator. But the proof of Model's theorem is a non-constructive proof with bound. So it says that it does not tell you how to find R and how to find generator, but it guarantees that some R and some generator exist inside some bound. So you can brute force this search over that bound to find the appropriate generator and R, but not efficient. If the size is too big, then you have to spend a lot of time searching it. But like for small coefficient, this is a very trivial task for a computer. So actually, you can look at like Sage Math, all this math software, and can find case by case. Pretty fast, I would say, by just brute force searching the generators. So we'll see an example of that later. So let's have a break here. And yeah, as promised, we should have class photo. So you can just line up outside. And probably I should use this as my background. Yeah, so of course, the apple banana question is not as important as the 1 million question. So let's talk about the 1 million question first. So some of you can hopefully solve it in the near future. Right, so what is number theory? Number theory means you want to study integers. And so what we are doing, first of all, still with elliptic curves. And of course, what I'm doing is all simplified, a slightly simplified version. So, well, I should say, like, we mentioned that we can always turn elliptic curves into this form. But in arbitrary field, you have to be careful because the formulas involve 2 and 3. So the method does not work if your field has characteristic 2 or 3 because you have to divide by 0. But in general, we'll just ignore those small cases and look at just general curve with integer coefficients. So we have integer equations, so we can talk about mod p. So we just look at the curve mod p. So this is okay if p is not 2 or 3. So any general cubic can be turned into this form. Yeah, so we are looking now in terms of number theory. I should ask this in the midterm, actually. But... All right, so we want to understand this equation, which makes sense, first of all. And also just notice that it must have finite solution only. Right, because we are mod p, so there are only p values of x, p values of y, you just test all of them. So there must be finitely many solutions only. So the hope is the local global principle, as we have always motivated, is that we hope that by studying an equation mod p for every p, we have some information on the original curve over q, or over integers, right? That's the hope we always want. So that's the local global principle. We try to study this curve over every p. And again, because after we reduce by p, this curve might be singular. You still have that discriminant. What's that? 4aq plus 27b squared. You still don't want this to be 0 after you mod p, so you want to assume that this is non-zero mod p, so that your curve is still singular, still non-singular. So we just basically impose the condition that p does not divide delta. We ignore those p, and there's only finitely many of them. Right? Basically, we ignore p where p divides delta, and only finitely many of them. So we'll, in the study of elliptic curves mod p, we have some special consideration when p is bad. This is called a bad reduction. This is called a good reduction for obvious reason. So we have to do something else, but we are not going to discuss that, and it's not important for us now. So now the question is, how many solutions do you expect to have by counting? So how many solutions to this equation do you expect to have mod p? Well, we can kind of treat the right-hand side, the x cubed part, as like uniform over all numbers, because we don't know what it is anyway. So what is the expected number? Very, very roughly counting. So we are finding basically the quadratic residue, right? So we are having equation of this form, where the right-hand side x cubed plus ax plus b is kind of random. We don't know what it is. But let's say it is just uniformly distributed, then exactly half of them is quadratic residue. Except how x in the rational gives quadratic residue. So we learn this, right? So we are running over through x from 0 to p minus 1. So exactly half of this will give quadratic residue. Exactly half of it gives quadratic norm residue, right? We learned this in chapter 2. So how many quadratic residues are there? There are p minus 1 for 2. So this is from chapter 2, right? There are exactly half of the numbers that will give me quadratic residue. And for each of them, I have two choices of y. For each of them, I have two choices of y. And this another half, we don't know. And then also we have the 0. Oh, I should say a, sorry. A. And when a is 0, I have one solution, y equals 0. And remember, we are talking about elliptic curves, which is supposed to be something projective. So we also have the infinity point. So infinity point is part of the elliptic curves. So how many points together total we have? We have p minus 1 plus 1 plus 1. So altogether, we expect that if things are so uniform, we should have p plus 1 solution to my equation on average, right? But of course, life is not that simple. So we definitely have error. So we will define the error term to be the difference between p plus 1 and the actual number of points on the curve. So this is the actual number of curves, actual number of points on the curve, difference by p plus 1. So first of all, this is an integer, plus or minus integer. And remember, this number includes infinity. So you also count infinity as one of the solutions. Now there's a theorem by Hesse, which gives you the bound of this number. And it says that AP cannot be too big, because I mean, p plus 1 is our expected number. And it turns out that it is not that much, it's not that bad. It is bounded by 2 square root p. If the curve is nice. So if the curve is nice, if P is nice, then this error is pretty close. It is just square root away from the actual expected number. And in particular, this will imply that this polynomial, 1 minus x plus px squared, is bigger than 0 always. Because the discriminant is negative. And it cannot be 0. So the discriminant a squared minus 4 b squared minus 4ac, b squared minus 4ac is negative. You just compute, just compute from this. Yeah, so this quadratic polynomial is always positive. And so with this, we now jump to analysis. Because now for each prime, for each good prime, I have a positive expression. So we can create a function out of this. So this is the L function of elliptic curves over a rational number. So this is the Euler product. L defined by over all the prime. And again, we don't want the bad primes, so just over all the prime that is good of this quadratic equation, but we plug in x equals p to the minus s. So this is slightly general than the Euler product. The Euler product we usually have is just 1 over p to the minus s, linear, but here somehow we have quadratic instead of linear. But yeah, that's the idea. And in any case, these are integer coefficients. A is integer, P is integer. So you can just use geometric series and rewrite this as a Dirichlet series also. Just like before, where this is integer. And this function converges absolutely not on real s bigger than 1 anymore, because you have quadratic. So it turns out that you can show this is converging over 1/2, 3 halves, 1 plus 1/2, 3 halves. Right, so this is the analysis side of elliptic curves. So from number theory, we look at mod P and then use this mod P thing to create the Euler product, which is now a analytic function. So it should be small s, sorry. So s is a complex number. And so the very recent result, just less than 20 years ago, says that this function can actually be continued to s equals 1 in general. Just like your theta function can be continued to whole complex plane, this is much harder to analyze, but it turns out that you can continue to s equals 1. And this follows very recently, 2001, from the modularity theorem, which is originally known as the Taniyama Sankok-Jichun, Taniyama-Shimura conjecture. So the Taniyama-Shimura conjecture is the main tool used to prove the Fermat-Last theorem. One of the special case of this conjecture is to use to prove Fermat's last theorem. And it basically says that yeah, I don't want to explain. Yeah, so basically it says that, I mean, the function has a modular form attached to this. So your function can be written as a modular forms somehow. So I won't explain that for any elliptic curves over Q. So there exists a nice modular forms relating to this L function. And modular forms by itself is something that is analytic. So you can have this extension. So I will not explain that. Otherwise, I will jump into a lot of timeless analysis thing. But in any case, this result says that I can now ask what happens for L at s equals 1. So one thing we know is that it has no pole at s equals 1, so the value is finite. The value of L1 is finite. And it turns out that it is finite, means you can write it Taylor series or power series, right? So it will begin with s minus 1 to some integer powers, and higher terms. So we know this. So when R is 0, it just means Ls is like a non-zero number. But when R is not 0, then L1s is 0. And so this is the order of 0. Order of 0 at s equals 1. And now you can solve the Birch-Swinnerton conjecture for the $1 million by showing that R equals R. That's the statement. So this big R, again, is called the analytic rank. So it tells you the analytic function's behavior at s equals 1. On the other hand, this is the algebraic rank, which, as we mentioned, is just the rank of the abelian group at Q. So this small r is constructed completely algebraically from the elliptic curves, while the big R is completely constructed by analysis, by complex analysis. So they are very different nature, and the conjecture says that these two numbers has to be equal. So that's the main statement of the conjecture, and it's, of course, some progress has been made, so only proven for R equals 0 or 1. That's the only progress so far. If the analytic rank is 0, then small r is 0. If the analytic rank is 1, small r is 1. And that is all we know about this conjecture so far. And actually, there are more deeper results. So for example, what is the coefficient CR? What is the coefficient? And it turns out that this coefficient also can be conjecturally written as some algebraic information of the elliptic curves called the Tate, I don't know how to pronounce, Shafarevich group thing. Yeah, so a lot of information about the elliptic curves are encoded in the first term of this series. Yeah, so this is the second Millenium problem mentioned in this class. We have Riemann hypothesis, and now this is the second one. Okay, so that's the money problem. Of course, we have to go back to the no money problem. So 99.99995% of people cannot solve this. But now, at least we are the 0.0005% that hopefully can. So this is so evil looking. You are asked to find positive, so whole values means positive integers. So positive integer solution to apple, banana, and pineapple equals 4. So let's try to simplify this. I stopped writing. I write already everything. So just first of all, rewrite the values. So A for apple, B for banana, C is not for pineapple. Why don't you use cherry or something? Yeah, so A for apple, B for banana, but C for pineapple somehow. Yeah, so we are asked to find integer solutions to this, but we can one step backward. Just ask, are there even any integer solutions to this or rational solutions to this? So first of all, if I have a rational solutions, this is a homogeneous equation. So if I scale everything, I still get a solution. So if I can find a rational solution, I can just clear the denominator and get an integer solution. So our goal is to find a positive rational solution. Okay, so we can clear the denominator and get integers. Now this is just an equation, so we can rearrange. We can clear the denominator, rearrange. We get something cubic, which is good, right? We get something cubic, so there is a hope that we can solve this with cubic techniques, which we just learned. And because everything is homogeneous, everything is degree-free, we can rescale by C to get back a generic cubic. And it also has a rational point, just a equals -1, b equals 0, c equals 1 is a rational point. And this point is bad. This point is bad because if you look at the original equation, you get 1 over 0 somewhere, right? You get a plus c is 0, b is 0. So this time is bad. So this is not really a solution to the original question, but it is a solution to my cubic, which means I have now a rational point, a cubic. I can turn it into a Weierstrass normal form by the previous method, some change of variable techniques. So the end result is this transformation. So x equals a bunch of rational thing, y equals a bunch of rational thing, which is invertible, by the way. So you can get back ABC from x and y. And with this change of variables, we get an honest elliptic curve. Y squared equals x cubed plus 109 x squared plus 224x. I use this form so that the right-hand side is 0 and x is 0, which looks nicer. I mean, the Weierstrass normal form, you cancel the x squared term, but here I cancel the constant term by just shifting. Right, so what is the goal now? So this equation comes from the original one. So if I can find a rational point in this elliptic curve, then I can find a rational solution to my original question. And if somehow you are so lucky that this ABC is positive, then you get the positive solutions to the original question. So now the question is to how to find rational points on these elliptic curves. And as I mentioned, you have a curve, you can compute the rank and the generators of the curve, not by hand, by computer, by Sage math. So this is how the curve looks like. It's not that bad. It's just, I mean, 400 thing on the right-hand side. And it passes through 0 because when x is 0, it is 0. So it passes through 0. So this is the elliptic curves. Looks like a fish tail, a fish with a tail. I mean, of course, this goes way up on the other side. So plug into the computer software, you see that this curve actually has just rank 1. R is just 1, which means you only have one generator for this curve. Which means that if you find this generator, every rational point can be constructed from this single number by this tangent line crossing line technique. And of course, the generator can also be computed by Sage, is -100 and 260. So you can just plug this back in and see that this is really a point. So where is that point? 100 is somewhere here, here, 260 here, somewhere here. So this is my P. So I have a rational point on the curve, which means by that equation, by this equation, I can get back ABC, which is 27, 114, 1114, and I can clear denominator and get integer solution. So this is like the smallest integer solution to your apple banana question, but you have -1, which is bad. We don't want negative answer. So what can we do? Well, we now know that every rational points on the curve are generated by P, so we just compute 2P. How do we compute 2P? Well, we compute 2P, remember, by drawing the tangent line, and then intersect somewhere in the 5th floor. We have an intersection, and then we have to reflect it down to LG5, and that is my 2P, right? The tangent line intersect at the 5th floor, so high above, and then you have to reflect all the way down. So the 2P lies in LG5, and you can compute the point to be this one. Yeah, so you can see you have a very negative y coordinate. So with this, you can find the corresponding ABC, which is 4-digit number. Still bad. We still have negative value. So we just keep doing. So you don't need tangent line anymore, because now to compute 3P, you just have P plus 2P and just draw the line, intersect, reflect. So I plug into the Mathematica, and I get 2P, 3P, 4P, 5P, still negative. So we know there must be a solution because that is the question. So we just continue. 6P, still get negative. 7P, 8P, and finally at 9P, we get a positive solution. And that is the smallest positive solutions. Right, so I draw this orange part here. So basically the orange part corresponds to positive solutions. So as long as your point lies on the orange part, you get a positive solution, and there are infinitely many of them, actually. There will be infinitely many solutions with positive ABC, and this will be the smallest one. And with that, I will end the number theory course. So thank you very much for enjoying it.